Ever been asked, is this tree height balanced? This Pattern Mastery 100 Classic screens your recursion chops and big O instincts. Many candidates compute height twice and time out. Today we'll solve balanced binary tree in a single post-order traversal, clean, linear, and interview ready, using the basic framework. We're given a binary tree root. A tree is balanced if, for every node, the absolute difference between the heights of its left and right subtrees is no more than 1. We must return true or false. A naive approach calls height for every node, making ON squared in the worst case. Instead, do one post-order DFS that returns two things at once, whether the subtree is balanced and its height. As soon as any subtree is unbalanced, bubble that up to stop extra work. Time ON, space OH for recursion depth, worst case ON, average O log n. Plan the helper DFS node. If node is none, return true, 0, recurse left, then right. If either side is unbalanced, return false, 0. Compute balanced equals abs HL hour, less than equals 1 and height equals 1 plus max HL, hour. Return balanced, height. The top calls balanced is the answer. Empty trees are balanced with height 0. Compute left and right. If either is unbalanced, stop early. Current node is balanced if the height diff less than or equal to 1. Compute height in the same pass. For a perfectly full tree, left and right heights always differ by 0 or 1 returns true. For a chain, linked list like 1 2 3 4, one side's height grows while the other stays 0. A node will have diff greater than or equal to 2 returns false. Each node visited once ON. Recursion stack OH. Here's the final complete solution for balanced binary tree. We do a single post-order DFS that returns balanced height from each node and short circuits on the first violation. Simple, linear, and interview ready. Level up your tree recursion by practicing diameter of binary tree, returns height while tracking the best path, maximum depth of binary tree, pure height computation, same tree, symmetric tree, paired DFS comparisons, lowest common ancestor of a BST/binary tree, propagate matches upward like our Boolean, and validate binary search tree, carry min/max bounds during DFS. These reinforce post-order reasoning, short-circuiting, and bundling multiple pieces of info in one traversal. Now, let's break down the first Python solution for balanced binary tree, a simple, clear approach to checking if a tree is balanced. Here we're defining a class called solution. LeetCode uses this structure so it knows where to find your method. Think of it as the container that holds our function. This line defines the main function, is balanced. It takes the root of a binary tree and returns true or false depending on whether that tree is height balanced. This is the function LeetCode calls for each test. Inside our main function, we define a helper called height. This helper will calculate how tall a subtree is. It's like measuring how many levels deep a branch of the tree goes. We start by checking if the node is empty. An empty node has no height at all. So if the node doesn't exist, we simply return 0, meaning the height is 0. If the node does exist, we compute the height of both the left and right subtrees. Then we take the bigger one, because the height of a tree is determined by its longest path. Adding 1 counts the current node. This height calculation is repeated many times throughout the tree, which is why this brute force approach can take ON squared time in the worst case. Now back in the main function, if the entire tree is empty, we consider it balanced automatically. So if there's no root, we return true. Here we calculate the height of the left and right subtrees and compare them. If the height difference is more than 1, the tree becomes visually lopsided, meaning it's not balanced. Notice that we call height again here, and each call recurses down the entire subtree. This repeated scanning is what contributes to the ON squared runtime. If that imbalance is detected, we immediately return false. If the current node is balanced, we still need to ensure that both the left and right subtrees are also balanced. So we recursively call is balanced on each side. Only if both return true do we confirm the tree is fully balanced. And that's how this algorithm works. It first measures the height of each subtree, then checks whether every node stays within the allowed height difference. Efficient, simple, and elegant. Test case check. Let's walk through it. Input root equals 3 9 20 null null 15 7. Alright, let's put our solution to the test using this tree input. 3 9 20 null null 15 7. This array represents a binary tree in level order form. 3 is the root. 9 is the left child, 20 is the right child. The nulls mean that 9 doesn't have any children. And finally, 15 and 7 are the children of 20. In this kind of problem, we're checking whether the tree is height balanced, meaning the left and right subtrees of every node differ in height by at most 1. For node 3, the left subtree rooted at 9 has a height of 1. The right subtree rooted at 20 has a height of 2, because of 15 and 7. The difference is only 1, still within the allowed range. Every other subtree is also balanced. Output: true. And that's exactly what our function returns, true. This matches the expected result, which confirms that our implementation correctly detects a balanced binary tree. So, our implementation is correct. The algorithm efficiently checks tree heights and balance conditions, ensuring every subtree meets the criteria, accurate and reliable. We begin by defining the solution class, the standard structure where LeetCode expects our method to live. This defines our main function, is-BST, which will determine whether the binary tree is height balanced. Inside the main function, we define a helper called height. This function computes the height of a subtree, and detects imbalance along the way. This clever structure allows us to check balance in on time by doing everything in a single DFS traversal. We start by handling the simplest case. If the node is empty, its height is 0. And we return 0 because an empty subtree has height 0. We recursively compute the height of the left subtree. If the left subtree is already unbalanced, it returns -1. And if that happens, we bubble up the -1 immediately, skipping all further work. Next, we compute the height of the right subtree. Same idea. If the right subtree is unbalanced, we pass the -1 upward right away. Here we check the balance condition at the current node. If the height difference between left and right is more than 1, this node becomes unbalanced. So we mark the entire subtree as unbalanced by returning -1. If everything is balanced, we return the height of this subtree, 1, for the current node, plus the taller of the two children. Finally, we check the height of the whole tree. If the helper returns -1, the tree is unbalanced. Otherwise, it's perfectly balanced. And that's how this algorithm works. It first sets up a height checking helper with early imbalance detection, then uses a single DFS pass to compute heights and verify balance at every node. Efficient, simple, and elegant. Let's test our function using this input. 1, 2, 2, 3, 3, null, null, 4, 4. These numbers represent a binary tree in level order form. The 1 is the root, the 2 2s are its children, and the deeper values like 3 and 4 show how far the branches extend downward. The null entries mean that no child exists at those positions. Left magnifying glass emoji. Quick logic check. Here's why the solution works. The algorithm checks whether the binary tree is height balanced, meaning no subtree differs in height by more than 1. In this input, the left subtree keeps extending deeper, 3 4. The right subtree also extends but not evenly. Eventually, one branch goes 2 levels deeper than its sibling. This imbalance causes the tree to fail the height balance condition. False, and that's exactly what our program outputs, false. This confirms that our code is working correctly and passes the test case. Our implementation is correct. The algorithm successfully detects that the given tree is not height balanced, efficient, accurate, and reliable. Big takeaway? Smart recursion isn't about writing more code, it's about returning more insight from each call. Bundling balance and height together is what makes this approach clean, elegant, and interview ready. Ever been asked if a tree is height balanced? Balanced binary tree. This one's a real interview classic. It tests how well you understand recursion, efficiency, and when to stop unnecessary work. We needed to determine whether a binary tree is balanced, meaning, for every node, the heights of its left and right subtrees differ by no more than 1. The goal was to return a simple true or false. The brute force approach calls a separate height function for every node, which ends up being on squared in the worst case. Instead, we optimized it by combining both the balance check and height calculation in a single postorder traversal. That keeps it linear, on time, and space proportional to the tree's height. We used a helper function that visits each node once. For each subtree, it returns 2 things, whether that subtree is balanced, and its height. As soon as one side is unbalanced, we immediately stop and bubble that result up, avoiding extra computation. We ran the logic in LeetCode, and it worked smoothly. No errors, no redundant height checks. The recursive calls handled balance and height together just as planned. After testing across multiple trees, every case passed, from perfectly balanced trees to skewed, chain-like ones. The solution produced correct results and ran efficiently.